Let's do some problems on computing Galois groups. Compute the Galois group. Of the following Galois extensions. So the first problem, so let's look at the Galois extension Q root 5 over Q. Okay, so first we should ensure that this is indeed a Galois extension. In this case, observe it's Galois. Well, that means two things, normal and separable. To check that it's a normal extension, we just have to realize that this field Q root 5 is actually nothing but the splitting field of an obvious polynomial. Look at the polynomial x square minus 5 with coefficients in Q. The splitting field of this, so what are the roots of this? Plus and minus root 5, and this field is generated by the roots of that polynomial. So by the usual definition of splitting fields, this is exactly the splitting field, so it's normal. And separable comes for free because the characteristic of Q is 0. So recall that if the base field is either characteristic 0 or a perfect field, then any algebraic extension is automatically separable. Okay, so what is a Galois group? So let's see, observe that we know the cardinality of the group. That's exactly the cardinality of its Galois group. And in this case, Q root 5 over Q is of course a degree 2 extension, okay, as we have seen before. Now, therefore, the Galois group must have two elements. So, well, what are they? One is the identity, of course, and recall that in this case root 5 and minus root 5 are the two roots of that polynomial. So, observe that the roots or the elements plus minus square root 5 are the roots of the polynomial, the reducible polynomial x square minus 5. Okay. And as you have seen earlier, if you are given an irreducible polynomial and you have an extension generated by all its roots, then there always exists an automorphism which sends any given root to any other root of this polynomial. Okay, so in other words, recall from what you have seen before, there exists an element sigma in. This fact has also come up in a lot of the proofs. So, sigma in the Galois group such that sigma sends this root plus root 5 to the other root minus root 5. Okay, so this is of course clearly not the identity element, and so what this implies is that the Galois group then comprises two elements. One is the identity, of course, the other is this element sigma. Okay, so it's isomorphic to the cyclic group with two elements. Okay, good. Let's do something slightly harder. So maybe we'll call this field K. It's generated by root 5 and root 7 over Q. Okay, again it's easy to see that this is Galois because this is the splitting field of, well, you can say it's a splitting field of two polynomials if you wish, x square minus 5 and x square minus 7, or equivalently it's the splitting field of the polynomial x square minus 5 times x square minus 7. Okay, so you can also say it's a splitting field of the collection of polynomials. Okay, and so that means it's normal, and as before, separable is just because of characteristic 0. Okay, so let's see what the degree of this extension is. That will tell us the cardinality of the Galois group. So we can think of this extension as being obtained in two steps. So let's say we first adjoin root 5 and then we adjoin square root of 7 to this field. Okay, so maybe we'll call this field as k1, which is q of root 5. Now what we already know is that q root 5 over q is of degree 2. Okay, and to that field k1 we are adjoining an additional element, square root of 7. Now we need to figure out what the degree of this extension is. Okay, so now I claim that this is also a degree 2 extension. Okay, why is that? Observe that, well, what's the polynomial that square root of 7 satisfies, right? We have to find out the minimal polynomial of square root 7 over the field k1. Okay, now what polynomial does it satisfy? Well, let's say is a root of, well, the obvious polynomial x square minus 7, okay, which I can think of as having either rational coefficients or coefficients in k1. Okay, so definitely this square root of 7 satisfies this degree 2 polynomial, but maybe it also satisfies a degree 1 polynomial. Okay, we don't know that. In other words, could it happen that square root of 7 already lies inside k1? Okay, if that happened, then of course k over q would only be a degree 2 extension. So therefore, this implies that k over k1 is at most the degree of g. Okay, it's at most a degree 2 extension, but claim it can't be a degree 1 extension. In other words, this element that we adjoined cannot already be inside this field q root 5. Okay, why is this? Well, this is sort of one of those nice little proofs like root 2 is irrational and so on. Suppose not, you would try and write. If not, then you should be able to write square root of 7 in terms of, well, of the form a plus b root 5, where a and b are both rational numbers, because that's what elements of q root 5 look like. And then you sort of square both sides of this equation and conclude that, well, this is 7 equals a square plus 5b square 2ab root 5. Okay, now the only way this equation can hold true is if, well, observe that root 5 is irrational. So all the other terms are rational. This implies that that term ab root 5 cannot occur. Okay, since all the other terms are rational, this would be the only irrational term otherwise. Okay, which means a or b is 0. Okay, but in that case, observe that this equation can't hold, right? So I've already said this is 0. Now if you look at what's left, 7 equals this. If I put a equal to 0 or b equal to 0, then I can't find a rational solution for the other guy. Okay, but observe, if b equal to 0, then I conclude a square is 7. Okay, which means that a is not, as we know, square root of 7 is not rational. So I'm using some facts that square root of 7 is not rational here. Similarly, if a is 0, this will imply that b square is 7 by 5, and therefore b is again, b can't be rational because b is the square root of 7 by 5. So we've used a couple of facts that square root of 7 and square root of 7 by 5 are not rational numbers. Okay, but that proof is the usual kind of proof, like proving square root of 2 is irrational. Okay, so that's basically what this claim involves. So we've shown this. Therefore, we conclude the following, that k over k1 is a degree 2 extension, k1 over q is a degree 2 extension. Therefore, k over q is a degree 4 extension. Okay, now what does that mean? That means that the Galois group k over q should have 4 elements. Okay, so of course the next question is, what group of order 4 is it? What's the structure of this group? So let's try and find some elements in this group, just like what we did in the earlier case. So recall, how do I find elements of this Galois group? Observe the following fact. Any element in this automorphism group, Galois group, is uniquely determined once I know what it does to the two generators, square root 5 and square root 7. So observe any sigma in any element of the Galois group is uniquely determined by its actions on the generators. Okay. Why? Because any other element of the field just can be expressed as a polynomial in these generators, and so sigma acting on that element can be uniquely computed. Okay, so let's see what are all the possibilities. So therefore, we'll try to list the possibilities for these two elements, okay, sigma of root 5 and sigma acting on root 7. So what are these? They are both elements of K, right? So both sigma root 5 and sigma root 7 are elements of this field Q root 5, Q root 7, Q of root 5 comma root 7. Now recall, as we have seen before, the same fact that we used earlier, that the minimal polynomial of square root 5. So observe that sigma root 5 must be a root of, so maybe we'll just call these numbers something like alpha be root 5 and beta denote root 7. Then sigma of alpha must be a root of the minimal polynomial of alpha over Q. Okay, this is the minimal polynomial of alpha over Q. Okay, so what does this mean? This means that, and what is this minimal polynomial? It's the smallest degree reducible polynomial that root 5 satisfies, and in this case it's easy to see this minimal polynomial is just x square minus 5. Okay, so therefore we conclude that when I act sigma on this element alpha, it has to be a root of the polynomial x square minus 5. Therefore, this can only be one of two possibilities. So, this can either be root 5 or minus root 5. Okay. Now, similarly, I also look at the other guy, beta. Observe that its minimal polynomial over Q is just x square minus 7. Okay. I mean, we have to show this is irreducible, but we have done examples like this before. Now, the roots of this polynomial are plus or minus square root 7. Therefore, analogously, when I take sigma, I act it on root 7, I can only get plus or minus root 7. Those are the only possibilities. Just like here, sigma of root 5 can only be one of these two numbers. Okay, so how many possibilities are there in all? Well, there are two possibilities for sigma of root 5. There are two possibilities for sigma of root 7. Between them, you get only 4 possible choices of sigma. So what this means in particular is that all these 4 must actually be elements of the Galois group, because the Galois group we have already deduced has 4 elements. Okay, so all these 4 possibilities must in fact be realized. Okay, so therefore the Galois group, so this is the Galois group of automorphisms of K over Q has the following 4 elements, okay, which are determined by what it does to each of them. So one of them is root 5. It says, okay, root 5 goes to minus root 5, root 7 goes to plus root 7. So we'll call this something sigma. Root 5 goes to plus root 5, root 7 goes to minus root 7. Let's call this tau. And then there is the composition of sigma and tau, which takes both of them to their negatives. And then there is the identity map, of course. So these are the 4 elements which belong to the Galois group, and this should be familiar. I mean, observe that each of them, sigma square, tau square are both identity, right? If you apply them twice, sigma tau and tau sigma are the same, doesn't matter which order you do it, and this is exactly the set of relations for the Klein 4 group. Okay, or if you wish, it's the direct sum of two copies of Z mod 2Z. Okay, good. So let's do another one, slightly more complicated, which is, let's take the base field again to be Q, and let's take the polynomial x cubed minus 5, and let K denote its splitting field of this polynomial over the base field Q. Okay, what does that mean? Well, I have to just take the roots of this polynomial. I know what the roots are in the complex numbers. It's a cube root of 5 and cube root of 5 omega, cube root of 5 omega square, where omega is the primitive cube root of unity. Okay, and maybe I'll give this real cube root of 5. So this is something, this has a real cube root of 5, call it alpha. Observe, this is also the same as you first adjoin alpha, then you adjoin omega to it separately, right? Because if I have alpha and I have alpha times omega, I can get omega from it. Okay, good. So what do we know about this field? Again, it's Galois because it's the splitting field already. It is separable because again its characteristic 0. Okay, now let's try and figure out what the degree of this extension is. So I start with Q and I need to go all the way up to K, which is Q of alpha comma omega. Again, I'll think of it as being realized as a successive tower of extensions. So I first adjoin alpha. Now what polynomial does alpha satisfy over Q? What is the minimal polynomial? So observe, alpha satisfies, well, alpha is the root of the polynomial x cubed minus 5, and in fact we know that this polynomial is an irreducible polynomial. It's irreducible over Q, for example, by using the Eisenstein criterion. Okay, so recall the Eisenstein criterion requires a certain prime number p that you use to prove the irreducibility. Here you can take that prime to be 5. So this prime divides well, it doesn't divide the leading term, it divides the constant term, and the square of this prime does not divide the constant term. Those were the conditions you needed for the Eisenstein criterion for irreducibility. So alpha is a root of this cubic polynomial, which is known to be reducible over Q, which implies that this extension here must be a degree 3 extension, okay, because the degree is the same as the degree of the reducible polynomial that alpha satisfies. Now what about the other one? Up here we need to look for what is the polynomial that omega satisfies over this field Q alpha. Okay, so this field, we are adjoining omega to the field K1 now. Now observe, omega satisfies, well, is a root of a certain quadratic polynomial, right? So recall the cube root of unity satisfies this polynomial, and this is, well, it has rational coefficients, but I can also think of the coefficients as coming from this larger field K1, right? So omega satisfies a quadratic polynomial with coefficients in K1, which implies that this extension here, so I don't know at this moment whether this is an irreducible polynomial or not, but whatever it may be, I know that this extension is at most degree 2, right? Now the claim is this is in fact irreducible, this polynomial is irreducible. So this is irreducible in even over this larger field K1x. Well, why? Because if not, if it's not irreducible, it has to factor into a product of two linear factors. This is after all quadratic, If not, then it would imply that then both roots belong to K1. So then it will imply in particular that omega comes from K1. Okay. Now, which is not true, because remember K1 is just Q adjoined a certain real number, which is alpha in this case. So I adjoin alpha, the answer is definitely real. It's a subfield of the real numbers. But omega is definitely not a real number, right? We know what omega is. It's got a certain non-zero complex part. So this is not real. Okay. So this is a contradiction. So this establishes that omega does not belong to the field K1. Therefore, this polynomial is irreducible. Therefore, let's go back. We can remove this less than or equal to symbol. This is exactly a degree 2 extension. So all told, therefore, it's a degree 6 extension. Therefore, K over Q is degree 6. And so this must also be the cardinality of the Galois group. So there should be 6 automorphisms of K which fix Q pointwise. So let's look for those 6. Okay, let's try and figure out, just like we did earlier, what those 6 must look like. And as before, we will try to analyze. So observe, as before, that if I give you a sigma in the Galois group is determined uniquely by its action on the two generators. In this case, the two generators were cube root of phi, which is alpha, and the cube root of 1, the complex cube root of unity, which is omega. So let's see what these things have to be. So observe for a start that what can sigma of alpha be? Well, what are the possibilities? Sigma of alpha can only be one of the 3 possible roots of the minimal polynomial of alpha. Okay. So possibility sigma of alpha has to be one of the 3 roots of the minimal polynomial of alpha over the base field. Okay, and what was that minimal polynomial? We already said this, it was x cubed minus 5. And so what are the 3 possible roots of that equation? They were just cube root of phi, cube root of phi omega, and cube root of phi omega square. So there are 3 possibilities for alpha. Can map, there are 3 possibilities for sigma of alpha. It can either go to alpha, alpha omega, or alpha omega square. Now analogously, we ask, okay, what about the other generator? What can sigma of omega map to? Okay, by the same token, now we need to ask, well, what is the minimal polynomial that omega satisfies over Q? Okay, so I have this element omega in K. Omega satisfies some irreducible polynomial over Q. Sigma must map omega to one of the roots of that irreducible polynomial. Okay, so it is one of the roots, again similarly, it's one of the roots of the minimal polynomial. Let's call it m omega of x. Okay, this is the minimal polynomial of this over Q. Now what is that? Well, it's actually the same polynomial, x square plus x plus 1. Right? We already know what polynomial omega satisfies over Q even. Right? It's just x square plus x plus 1, and this is of course irreducible. Okay, for the same sort of reason that we gave earlier. It's irreducible over K over Q as well as over K1 for the same sort of reason. If not, then omega would have to be an element of Q, okay, which we know for sure is not the case. Okay, so therefore sigma of omega can either be omega or the other root of this polynomial, which is omega squared. Okay, now again there are how many possibilities for sigma? It can map alpha to one of these 3 choices. It can map omega to one of these 2 choices. Put together, there are 6 possible choices maximum. Okay, all choices need not always be consistent. Okay, but these are the maximum possible choices. There are only 6 of them. Okay, but we already know that the Galois group has exactly 6 elements, which means that all 6 of these possibilities must actually be, really possible. They must arise. Okay, therefore, what we conclude is that all 6 possibilities do arise, okay, when you look at the possible elements of the Galois group. So let's write out these 6 elements. So let me, like we did earlier, let me say alpha goes to alpha, let's say omega goes to omega square. So let me give this map a name. It's called the sigma. Okay. Now let's look at another one. Alpha can go to alpha omega. It's called this tau, and omega goes to omega. Okay. Then let's look at what are the other possibilities. So the remaining elements can more or less be obtained by looking at various compositions of sigmas and taus. Now just with this sigma and tau, observe many things, that if I, for example, compose sigma with itself, what is sigma composition sigma? Well, this map, which we'll call sigma square, takes alpha to alpha to alpha, right? I'm composing it twice, omega goes to omega square, and when I compose it once more, what should it do? Well, omega squared, so it goes to omega squared squared. Okay, when I apply sigma again, but that's omega to the 4, which is omega. Okay, therefore, what do I conclude? Sigma square is therefore just the identity map, because it maps both alpha and omega to themselves. Of course, it maps q to q, right, as a pointwise identity. Now, similarly, if you compute tau cubed, you will notice that it's again the identity map. And if you compute sigma tau sigma inverse, you will notice that this is tau square. Okay, so I'm sort of leaving these two here as exercises for you to compute. So what we have generated are, well, 5 elements, I suppose. Sigma tau, well, okay, not quite. We have only looked at sigma and tau as elements, and then we are looking at the various relations that they satisfy. So observe that this final equation here tells you that this group is non-abelian, because sigma tau is not the same as sigma tau sigma inverse should have given you tau if sigma and tau commuted with each other. Okay, so this implies that sigma and tau do not commute. Okay, and of course, all this fuss is more or less to say that this is a non-abelian group of order 6, and the relations are probably familiar already. This is the group S3, or if you wish, it's the dihedral group with 6 elements, another way of saying the same thing. Okay, so observe that these 6 elements are exactly the automorphism group of K over Q. In this case is just the symmetric group S3. And you can write out all the 6 elements if you wish. It's identity, tau, tau square, then there is sigma, sigma tau, and sigma tau square. So they will realize these 6 elements will give you all the 6 possibilities. Okay, alpha mapping to one of the 3 alpha omega square, omega mapping to one of the 2 possibilities omega or omega square. Okay, now recall that what are the subgroups of this? What do the subgroups look like? So let's try to bring in the fundamental theorem of Galois theory here. So what do the subgroups of S3 look like? So let's I just wrote out all 6 elements, and it's easy to see that this, for example, is a subgroup of order 3. Okay, it's the only subgroup of order 3, the alternating group. And there are a few subgroups of order 2, right? Identity sigma, identity with sigma tau, identity with sigma tau square. These are 3 subgroups of order 2. Okay, and that's it. So let's write out all the possibilities. There's the identity, let's just call it E in this case. Then there is, maybe we should just write it as ID. So it's the identity subgroup. Then there is identity sigma, sigma tau, identity with sigma tau square, Okay, these are the order 2 subgroups, and then there was an order 3 subgroup, identity tau square. Okay, and then finally the full group itself. Okay, just the group S3 in this case. Now let's draw the inclusion relations among them. So this contained in this is contained in this. So when you draw a line, it just means that the subgroup on top is contained in the subgroup on the bottom. Okay, so this is the partially ordered set whose elements are the subgroups and where the partial order is just one of containment. So I've drawn them here. Now what does the fundamental theorem of Galois theory say? That this is in one-to-one correspondence with the subfields of K. Okay, well, I should actually say the intermediate subfields of this extension, meaning subfields which lie between K and Q. Okay, so let's see what are the various possibilities. We already know what this map is, right? So given a subgroup, recall what the fundamental theorem of Galois theory says. If I give you a subgroup H, you are supposed to send it to the fixed field of H. Okay, the elements of K which are pointwise fixed by every element of H. Okay, so now I know that some things are obvious. If I take the identity, then the identity fixes every element of K, so that goes to K. If I take S3, then the only elements of K fixed by all elements of the Galois group, that's going to be the base field, right? So that was the definition of a Galois extension, if you wish. Now I have K and Q at the two ends, and then I have, well, there should be some subfields corresponding to these four subgroups. So let me call it K1, K2, K3 and K4. Okay, so again I should have now inclusion relations in the same way. Okay, I should be able to find subfields like this, which are all which have the same inclusion relations. Okay, so recall this is an inclusion reversing bijection between these two sets. So the question is, what are these K1, K2, K3 and K4, right? Let's try and figure them out. They are the fixed fields. Now what is K1? Well, K1 is by definition the fixed field of the subgroup whose elements are identity tau and tau square, right? Now what do we know? Well, what is tau? I sort of said what tau does. It maps alpha to, let's write it out again, alpha goes to alpha omega, omega goes to omega. Okay, so definitely omega is fixed by tau because omega maps to itself. Omega square also maps to itself, right? I mean, any multiple of omega will map to itself, any power of omega. Omega is also fixed by tau square, right? So observe tau and tau square both fix omega. So one thing we know for sure is that Q and omega are both inside this field K1. Okay. Now what is Q omega? Well, what's the degree of Q omega over Q? So recall we have already said this, omega satisfies a degree 2 polynomial over Q. So this is just a degree 2 extension. Okay, now we'll soon see that it's actually equality there. So let's move on to the other one. So what is K2? K2 is the fixed field of identity with sigma. Okay, now identity with sigma is what are the possibilities? Sigma maps alpha now to alpha, maps omega to omega square. So by the same reasoning as before, definitely this fixed field contains Q and it contains alpha. So it contains the field Q of alpha. Okay, and how big is that? Q alpha over Q is, as we saw earlier, alpha satisfies a degree 3 irreducible polynomial. So this is a degree 3 extension. Okay, so now let's go back and use another part of the fundamental theorem of Galois theory. So recall again fundamental theorem. Says the following, if I have this subgroup H, then the cardinality of H is actually the same as the degree of the extension K over KH, right? So this was one of the parts of the fundamental theorem. So let's use this now because it gives us some valuable information. So what does it say? Let's look at the subgroups. So these are the three subgroups here whose cardinality is 2, right? So identity sigma has cardinality 2. So it says that K over K2, right? This extension must have degree 2. Okay, this is a subgroup of cardinality 2. So this extension must have degree 2. And similarly, this extension must have degree 2. Similarly, now this is a subgroup of cardinality 3. Therefore, this extension must have degree 3. Okay, so that's what we conclude. Now, observe that the total extension, which is K over Q, that we already know what its degree was. That was the original Galois extension whose degree was 6, right? So that allows us to sort of conclude that to calculate the degrees of these other extensions by using the tower property. So for example, I go from Q to K1 to K, the total degree must be 6, so therefore this must be 2. Now total must be 6, so these 3 must all be 3's. Okay, so I can work out all the degrees of the extensions by using this other part of the fundamental theorem. Okay, now let's go back and revisit what we know about K1, K2 and so on. So K1Q I know is degree 2. Okay, now what do I know about K1? I know that K1 contains Q omega certainly. K1 is at least as big as Q omega, but Q omega over Q is already degree 2. Okay, so by degree considerations, by degrees, I conclude that K1 cannot be any bigger than Q omega. That's about it, because already I have gotten degree 2. Okay, by the same token, I take K2, which is, it contains Q alpha for sure, but the degree of K2 over Q is 3, right? So I have already gotten 3, I can't get anything larger, so this can only be Q alpha. Okay, and similarly, if you look at the other two fields, K3 similarly will be Q of alpha omega, and K4 turn out to be Q of alpha omega square. Okay, so these are all the degree 3 extensions. So what we have really is we've sort of looked at the entire fundamental theorem of Galois theory in this case. Okay, good. Now let's do one last computation, and this time not over the field Q, but rather over a finite field. Okay, so compute the Galois group of the extension Fpn over Fp. Okay, first let's check that this is Galois again. So we need what? Normal and separable. Normal is easy because recall Fpn more or less is the splitting field. This is how it was constructed if you wish. You just take this polynomial x raised to the p to the n minus x, and in fact all the solutions, the roots themselves form a field. So for sure it's the splitting field of this polynomial. Okay, this polynomial splits completely over this field. So therefore it is normal. And separable, recall, again comes for free in this case because we had shown that Fp being a finite field is perfect. Okay, therefore any algebraic extension of a perfect field is automatically, any algebraic extension of Fp is automatically separable. Okay, so it's Galois for sure. So the question is, what's the Galois group? Well, we know the cardinality Fpn over Fp, recall, is just a extension of degree n. Therefore the Galois group, the automorphisms which fix Fp, this must have cardinality n. So again we could try and find some elements of this Galois group. Now since we didn't quite construct Fpn as Fp adjoined with some elements, rather we did something more indirect, wrote it as a splitting field of some polynomial and so on. So we don't quite know, given an element of Fpn, what exactly is its irreducible polynomial and so on. So the sort of analysis we did for the first 3 problems won't work here. But fortunately, we actually have some ready-made elements of the Galois group. So recall, when we talked about perfectness and so on, we introduced what we called the Frobenius map. Okay, so what was the Frobenius? Well, because Fp is perfect, it's an automorphism for Fp to the n, in fact. So recall, the Frobenius automorphism of Fpn is just the map. Okay, let's call it phi, which takes any element to its pth power. Okay, we had shown that this is a field automorphism. Because Fpn is finite, this is, it's always injective. Because Fpn is finite, this is surjective as well. So it was an automorphism. Okay, so here's at least one element phi, it's an automorphism of Fp to the n. Observe that if I take an element A which comes from the base field Fp, then phi of A is actually equal to A. Okay, because remember, elements of Fp, they satisfy A power p is A, right? So every element of Fp certainly satisfies this equation. Okay, now why did I say this? This therefore means that phi is an element of the Galois group. It not only is an automorphism of Fpn, it also fixes every element of the base field Fp. Now the claim is that this element phi that we have constructed, let's try and compute its order in this group. Okay, it's an element of the Galois group. What is its order? Okay, the total order is n. So the order of this element in the Galois group has to be some divisor of n, but the claim is that the order is exactly n. Okay, in other words, the Galois group is cyclic. Okay, so what does that mean? Here's what I'm going to prove, that if I compose phi with itself k times, suppose I compose phi with itself k times to get identity, then this means that this can't happen if k is smaller than n. So let us just say this. This can't be the identity if k is any number that's smaller than n. Okay, k times. Okay, why is this? Well, let's try to see what this would mean. Okay, so if phi to the k is identity, so phi to the k is just this composition. What does this mean? This means that how do I apply phi? I keep so when I act it on an element, phi to the k acting on an element A is just a to the p, the whole to the p, the whole to the p, and so on. So it's a to the p square, a to the p cubed, etc. So this is just a to the p to the k. Okay. So if this is equal to a, so this is on the one hand, the identity map is just a. Okay. So these are both equal to each other, implies that, so this is for every element a of my field Fpn. Okay. Therefore, what I am claiming is a to the p to the k is equal to a for all elements of Fp to the n. Okay, but observe that if you look at this polynomial, x to the p to the k minus x, consider this polynomial. What's the degree of this polynomial? It's just p to the k. Okay, and what we are claiming is that this polynomial has p to the n roots, right? Because every element of Fp to the n is a root of this polynomial. Okay, and now what we are concluding is that this polynomial has p to the n roots, okay, in this extension field in Fp to the n. Okay, this is clearly impossible if n is bigger than k, right? You can only have p to the k possible roots maximum. You can't get p to the n where n is bigger than it. Okay, so that's the contradiction. So that tells you that phi to the k can't possibly be the identity if k is strictly smaller than n. Okay, so what this means is, and of course phi to the n is identity is clear. Okay, also observe, more or less by the definition of the finite field, phi to the n is surely identity, since a to the p to the n minus a is 0 for all a in the finite field. Okay, so the conclusion is that the Galois group, the automorphism group of fp to the n over fp, is exactly the cyclic group generated by phi. Okay, what are the elements? Identity, phi, phi square, and so on. Phi to the n minus 1. Okay, so these are the elements of the Galois group, and again, sort of by a similar token, one can work out the fundamental theorem of Galois theory. So will tell you that the subgroups of this group are in one-to-one correspondence with the intermediate subfields, and if you sort of see what are the subgroups of a cyclic group, well, they can only look like they are also cyclic, generated by some element phi to the d, right, phi to the n, okay, where d is some divisor of n. Okay, so you can look at these groups, and so if you take this, maybe we should call this something h sub d. So what are the possible subgroups? They all look like this, h sub d, where d divides n. And you can ask, oh, what's the fixed field of this group, right? So this is my fpn, and I need to ask, oh, what's the fixed field of this subgroup? Well, by definition, it is all those elements which are fixed. It's enough if it's fixed by phi to the d, then it will be automatically fixed by all the others, right? So this is almost like the calculation we just did. So what is this? This is just all those elements A, such that a to the p to the d minus a is 0. Okay, so it's all those elements of fpn which satisfies this property. And recall that from the earlier discussion of subfields of finite fields and so on, this collection here is actually this HD, the fixed field, is it's the copy of, it's the unique copy of the finite field f to the p to the d that lives inside f to the p to the n. Okay, so recall, go back and look at that earlier lecture. For every divisor d of n, you can find a unique copy of fp to the d inside fp to the n. And how do you get that copy? You just take those elements of fpn which satisfy this exact equation, a to the p to the d minus a is 0. Okay, good. So that sort of ties it up nicely with what we have seen earlier. And you can also draw, for example, the same sort of diagram which we did. You can see what are the divisor relations and so on. And similarly you can get something on the other side which tells you how the various subgroups live inside fpn. Okay, so I'm going to leave that as an exercise for you to figure out. So these lines here are just going to go between two numbers d and d dash, whenever d divides d dash. That's going to be those lines there. Okay.